Okay, good morning again. So yesterday I introduced some notions from Cauchy theory, Jensen measures and so forth, Cauchy boundary. And we want to see now why these are useful in studying property PQ. So here is a proposition. Two, I think according to my notes, hope it's correct. So X is compact in Cn. The following are equivalent. One X satisfies property PQ. Two, PQ of X, that is, those functions that can be. Yep.
So what does it mean for arbitrary compact to satisfy the property? Was it property a property of the boundary of the
Maybe that's how we originally defined it, but the definition makes sense for any compact set.
Is this a neighborhood use?
Yeah, for every M, there is a neighborhood use of M, of X, and a function lambda M between 0 and 1 with the condition on the Hessians. Right. Okay, so X satisfies property PQ. Then this subset of the continuous functions of X, PQ of X, these are the continuous functions that can be approximated uniformly on X by functions, in the case Q equals 1, by functions plurisubrahmonic in some neighborhood, and otherwise in PQ. That's actually all continuous functions. Thirdly, the Q-Cauchy boundary of X is all of X. That is, every point of X has the property that the only Q-Jensen measure for the point is the point mass. And 4, it actually suffices to be able to approximate one particular continuous function, namely the function minus mod C squared belongs to P sub Q of X. All right, so let me give sort of partial proof. Well, mostly proof, I think. But just want to do it for Q equals 1. Just to simplify the notation, that's all. Everything I say works verbatim for general Q, but, well, it turns out the equivalence of 1, 2, and 4 is essentially just unraveling the definitions. Getting 3 into play requires a little bit more. So let's have a look. 1 implies 2. Okay, so I need to take a continuous function and I need to approximate it by functions in here, right? Now, we can assume F is, say, twice continuously differentiable in some neighborhood of X. Just continuous functions on X can be approximated by even smooth functions on, right? So if that's, it suffices to approximate such functions. But for such a function now, I can find a lambda m in PQ, such that 0 less than or equal to lambda m. But now I'm not going to take less than or equal to 1. I'm going to take 1 over m here. Remember, we said the bounds don't really matter. We can, so I take such lambda m and such that the Laplacian, well, not quite the Laplacian, but the Hessian d square lambda m dCj dCk bar plus the Hessian of f is going to be greater than or equal to 0 on x. Just because this is C2, x is a compact set, so there's a lower bound on the eigenvalues here. And so if I choose my lambda m, so I have this, and so that the Hessian is as big as it needs to be to make this positive, right? Yeah, but now we're done. Let's look at f plus lambda m. Oh, I had q equals 1. That's why I had the Hessian. I'm sorry. So actually here, why I had Laplacian, you can just take the Laplacians. No, still take the Hessians. Sorry. It's not that early in the morning. I should, no excuse. Anyway, but now take f plus lambda m. This is in PQ. Because of this. It's bigger than equal to 0. If you want to, you can get it, if you make it a little bit bigger than 0 on x, you have bigger than equal to 0 in the neighborhood. And so this will be in px, but of course lambda m is small. So this function is close to f, right? So if we do this and let m go to infinity, these guys will go to f. Then two implies 4 is, of course, trivial. Is everything okay? It's okay. So that was 1 implies 2. 2 implies 4 is trivial, right? 4 implies 1, so 2 implies 4 is trivial. Let's see how 4 implies 1. Right, so I know I can approximate this function, and I want to establish property P1. Well, if I can approximate this function, then I can also, for every positive number m, I can approximate minus m times mod c squared, right? So there exists a lambda in PQX with, so that's close to, so that lambda minus mc squared is small. And so I can certainly take this to be between minus 1/2 and 1/2. I don't even care about particularly close. Right, but 4 says I can choose my lambda or lambda sub m so that this is arbitrarily small in absolute value, so certainly can make it between minus 1/2 and 1/2. Yeah, but now look what we've written. This is lambda plus m mod c squared. So this is going to be a function with a big Hessian, because lambda is Plurus of Riemannic, and the Hessian here is going to be at least m. So the Hessian in this function is at least m, right? Now it's not between 0 and 1, but if you add 1/2 to it, It won't change the Hessian. It's going to be between 0 and 1, right? So that was really all just unraveling the definitions. So now, how do we get 3 into play here? Well, the 2 implies 3 is clear because if we take a point C in X and we take a Jensen measure, if 2 holds, then the continuous functions have to sub-average with respect to this measure. But of course, that means the measure has to be concentrated at the point, right? So in other words, we have 3. So the only thing here that takes a little bit of doing is 3 implies, the other conditions, and in fact, the way I'm going to do it is 3 implies 2. But so let me know 2 implies 3 is clear. 3 implies 2 that uses something that's usually called Edwards' theorem. Which in this context says the following. The soup of, well, I should take a continuous function. Then 2 quantities are equal. One is the soup over the numbers lambda of C, where lambda is in in P1 of X, now that Q is 1, and lambda less than or equal to F on all of X. This soup equals an inf, namely the inf over the integrals over X, F d mu, where mu is a Jensen measure at the point C. And notice in this theorem, one direction is clear, namely the soup is always less than or equal to, because lambda stays below F on the one hand, and lambda is in P1. Mu is a Jensen measure, so lambda of C is less than or equal to this integral, but with lambda, and then lambda stays below F, so it's less than or equal to what you get here with F. Mu is a probability measure. So that direction is obvious. The other direction is not obvious, but it's the kind of thing having to do with sort of convex functional analysis, separation of convex sets, and so forth. So I'm not going to go into the details, but it's not terribly hard. A nice reference for all of this is an old monograph by Gamlin, which is called Uniform Algebras and Jensen Measures, which is probably 40 years old or so, but there is a new edition that came out relatively recently by, I think it's maybe the London Mathematical Society Press, either that or Cambridge. And this is proved within the first, 20 pages or so, so it's not. But so if we have this, now how can we, if we have a continuous function, we have 3, how can we get 2 out of this? Well, so if we have a continuous function, if 3 holds, then all the, there's only one Jensen measure here, the point mass at the point. And so this, if 3 holds, this is just f of c, right? Because the point mass at the point C is the only Jensen measure. So that's just f of c. So then what this says is the soup over these guys for every point c is f of c. So now here's our continuous function. Here's x. So given an epsilon, I can find the lambda in here so that at the point c, this is going to be close. Then just by continuity, there's going to be some neighborhood where it's close. In other places, maybe not, but here it is. Neighborhood will depend on epsilon, of course, that's fine. But still, I can do this for every point. X is compact, so then I get finitely many of these neighborhoods. For each of the neighborhood, I have one of these lambdas. But now if I take the maximum over these finitely many lambdas, that's still a function in P1 of x, because maximum over supermonic, right? And that maximum is then going to be close everywhere from below. And it's not hard to see that the limit is actually uniform. Well, in fact, it comes out of this argument. Okay, so that takes care of that. There is a useful characterization. We may not use it this week, but I'm going to write it down anyway. Of points in the Cauchy boundary of x that is provided by the abstract theory. So I'm not going to give a proof. So the notations are as above. Well, set up as in proposition 2. Then 1 C belongs to the Cauchy boundary with respect to PQ. This is if and only if 2 for every f in Cx, there exists lambda in PQ of x with lambda of c equals f of c, and otherwise lambda is less than or equal to f. So for every continuous function f, there exists a function lambda in PQ of x that in some sense kind of peaks at c with respect to f, right? And peaks in a weak sense. Here is not a strict equality. And right, it's with respect to f in the sense that at c it agrees with f. Everywhere else it at least doesn't exceed f. Like I said, this follows from sort of the abstract theory, and again, Gamlin's book is a good place to find these things. All right, so now I'm going to come to part 4. We actually want to compute some examples, if you will, and we're going to do that on Hartogs domains in C2. These are domains that have rotational symmetry in the second variable. I'm not going to consider general such domains, but we're going to have a simplified setup. So we're going to take Hartogs domains. Over the unit disk in the plane or any other disk. These are domains of the form omega. It's going to be point CW in C2, of course, where mod W squared is less than or equal to e to the minus phi of c. So if this is the disk down here, then for each point C, you have a disk in the W variable, right? With radius given by square root of this. So And depending on how this behaves as C goes out to the boundary of the disk, you might have something like this. When we here sort of pretend this is mod W. Now, actually, I want to be in a situation where this domain is smooth, where mod C is 1. So it should look something like this. And we're going to insist here that near mod C equals 1, this phi of C should just be log 1 minus mod C squared, I guess minus the log. Then if you put this in here, you get mod W squared less than 1 minus mod C squared. So down here, where W goes to 0, this is going to look like the unit ball. And certainly going to be smooth, and it's going to be strictly pseudo-convex there, because the unit ball is. Now, and then inside, at this point, I don't care. Let's take it C infinity. On the, of course, not on the closed disk if I want this, but on the disk. All right, let's see. I can go through here, up to here, or one more. Oh, okay. Oh, plenty of space. Well, now, I would like the domain to be pseudo-convex. So let's compute what this means. Now, it's not going to be a problem here in these parts where the domain looks like the ball. Those points are pseudo-convex points. But for points on the inside, I can take the following defining function. I can take rho of C and W equals mod W squared minus e to the minus phi of C. This will be a defining function, not globally, but over D. It's going to be smooth. And so, well, we need to compute the Hessian. ECK bar. If you compute this, well, let's first do the sort of easy part. The term here, well, there's always this issue. I mean, this is C1 is Z and C2 is W, right? So the term here is going to be D square rho, dW bar. So W only enters here. This is W times W bar. So if you do D bar on this, you get 1. If you have mixed derivatives, you're going to have 0 because, well, it's separated like this. And so finally, we do have to differentiate this term with respect to DC and DC bar. And you just do that, and what you find is it's minus e to the minus phi d phi dc squared plus e to the minus phi, and then the Hessian of phi. And then the vectors we need to put into this Hessian need to be complex tangent vectors, right? So for complex tangent vectors, say, let's call them zeta 1, zeta 2. Well, they need to satisfy, so they need to satisfy d by dc of the defining function zeta 1 plus d by dw of the defining function zeta 2 should equal 0, right? And so if you compute that here, you're going to have e to the minus phi d phi dc. So I'm differentiating this with respect to c, zeta 1 plus differentiate this with respect to w, you get w bar, zeta 2 should equal 0. So the complex tangent space at a point CW is spanned by let's see, I can take, if I take zeta 1 to be 1, I can always solve for zeta 2 on the inside because W is not 0, right? So 1 and then whatever you get here minus e to the minus phi d phi dc over W bar. So then for pseudoconvexity, I need to take this spans the complex tangent space is one-dimensional. I need to take this vector, plug it into the quadratic form here, and the result should be non-negative, right? So plug into, let's call it star, and well, you just do that, then you compute, and what you get is you get e to the minus phi d square phi. Oh, well, there's a point one should consider here, so let me write out the whole thing. It's going to be e to the minus phi. There's going to be a d phi by dc mod squared minus the Hessian dc bar plus e to the minus 2 phi d phi dc mod squared downstairs w squared. Okay? Well, now we're looking at a boundary point. This equals, on the boundary, this equals e to the minus, where's the defining function here, equals e to the minus phi. So an e to the minus phi factor here cancels, then let's see. Oh, I forgot a sign here. This wants to be a minus. Okay, now we're in business, right? An e to the minus phi factor cancels here, so I have e to the minus phi d phi dc mod squared with a plus here with a minus, so they drop out. So what remains is just e to the minus phi d square phi dc bar, and that's 1/4 e to the minus phi, and it's just a Laplacian of phi. Okay, so in order for our domain to be pseudoconvex, phi has to be subharmonic, and you can check this portion near the bottom is. So it has to be subharmonic. Also, the weakly pseudoconvex points are going to be precisely the points where that Laplacian equals 0. Okay. Now, the examples I want to look at are meant to illustrate the sort of relationship between disks in the boundary, property P1, and compactness. It is, unfortunately, more subtle than one might have hoped originally. Lemma 4, omega is above, then B omega contains an analytic disk. If and only if capital K, well, I need to say what capital K is, so let me do that back over here. Capital K should be the point C where Laplacian of phi vanishes. If K has non-empty, interior, just in the Euclidean sense. Let me not write down the proof, just sort of verbally indicate it's not hard to prove. So suppose there is a disk in the boundary. So you have this map from the unit disk into C2 that maps into the boundary. The tangent to the disk is going to be a weakly convex direction. That's always the case, and I think I wrote it in the exercise set to actually verify that. It's not hard to do. So in other words, all the points of the disk in omega, all the points of the disk will project down to points of K, right? Now, if you look, this vector spans the complex tangent space, so the first component is non-zero. So that tells you that this projection is going to have non-empty interior. In the other direction, if K has non-empty interior here, take a little open set, like a little disk. Well, how do you map into the point here? You map, C goes to e to the minus phi of C, right? Now this is not holomorphic, but on this little disk, because it's inside of K, phi of C is harmonic, and so take the harmonic conjugate, right? So it's plus or minus I times the harmonic conjugate. That still leaves you in the boundary because, right? And that's going to be your disk in the boundary.
In that open set.
Right. Well, yeah. Yes. Okay. Now, on the other hand, let's look at the boundary satisfying property P. So omega is again as above. B omega satisfies property P1. Note we're in C2, so there is no higher Q's. Property P1, if and only if K satisfies property P1 in the complex plane. Now, this is only a portion, half of this proposition. I will finish it in a moment. The point is that the set K in the plane satisfying property P1 can also be expressed in terms of a certain non-empty interior, but not with respect to the Euclidean topology, but with respect to the fine topology. That is the coarsest topology that makes all the subharmonic functions continuous. So let me write this down first, and then we'll finish up with the lemma. This is proposition 4. Then K satisfies property P1 if and only if 2 K has empty fine interior. Now this I will not prove. It's outlined, I think, in the notes how to get that. There's a whole list of properties which are also of interest, but that's the one we're going to use. So, i.e. here, if and only if the fine interior, which I indicate with a subscript F, the fine interior of K is the empty set. So then we could have phrased the lemma 4 sort of the contrapositive. The boundary contains no analytic disk if and only if K has empty interior, right? The boundary satisfies property P if and only if K has empty fine interior. Now the point is, the fine topology has many more open sets than the Euclidean open sets, and so what we get immediately from this is that property P1 can fail without there being a disk in the boundary. Right, the disks, I forgot to point this out. I think, yeah, the proposition is erased now. But remember, property P1 meant all continuous functions could be approximated essentially by subharmonic or plurisubharmonic functions. Clearly, if you have a disk in the boundary, that's going to give you a contradiction to the maximum principle. So disks in the boundary are the obvious obstructions to property P1, but there are more subtle ones, and this illustrates that. That is too bad, but that's the way it is. Okay? All right. I don't want to give the proof here. Basically, what one does is, well, suppose you have property P1 on the boundary here, and what really matters is the set W of the weakly pseudo-convex boundary points that projects onto K. Then, if you need to approximate a function down here, you transport it up there, use this equality on the boundary, and so forth, and you can transfer functions up and down. All right. Now some of those computations that you have to do are not totally trivial, but anyway, they can be done. All right, so now we can construct various interesting examples, namely, like I said, there exists K with the Euclidean interior empty, but the fine interior non-empty. I don't want to write down such a set, but I've outlined the construction actually on page 8 of the handout, item 5. And there is a bad typo there. I wrote there, a compact set in the plane with empty fine interior, but non-empty Euclidean interior. such a set does not exist. What I meant to say is a compact set in the plane with non-empty fine interior, but empty Euclidean interior. And it's not, if you don't do these things every day, it's not something you just write down. You sort of have to know the tricks of the trade. Anyway, such sets exist. So then we have P1 can fail, just for the record, without disk in the boundary, right? Second example, one can show for every k in C, or if you want in the disk, unit disk, doesn't really matter, with non-empty fine interior, there exists omega as above, well, there exists omega such that K, the set where the Laplacian of phi equals 0, and the Debraj-Neumann operator is not compact. That is not so easy to construct. This was done by C.G. Fu and myself around 2000. It is sort of an involved construction, but it can be done. So in particular then this shows that failure of compactness for the Debraj-Neumann operator can happen without disks in the boundary. So there too, obstructions to compactness can be more subtle than disks in the boundary. I mean, we had this example, remember, but that had D cross D, but there were lots of disks. And I said, the problem is the disks. In fact, we're going to see, at least in C2, if there is a disk in the boundary, compactness fails. But this shows, again, the obstructions can be considerably more subtle than just disk in the boundary. And finally, you can produce here examples where the set of weakly pseudoconvex points is big in the sense of having big measure, and still you can have a compact Debraj-Neumann operator. So the philosophy is, strictly pseudoconvex points are good. They're good for property P and so good for compactness. So weakly pseudoconvex points should be sort of obstructions, at least if too many of them. You can have many in the sense of having positive measure on the boundary and still have compactness. Namely, you can take a K with the fine interior empty, but it's Lebesgue measure in the plane strictly positive. And so in this construction, those are going to give you the weakly pseudo, K is going to give you a set of weakly pseudoconvex points up here, also of positive measure. Okay. Well, so What this still doesn't answer for these domains is what is the exact relationship between property P1 and compactness, right? Of course, we know P1 implies compactness. We know compactness can fail for sort of subtle reasons. It turns out to be true for Hartogs domains in C2, and let's state this as a theorem. P1 and compactness are actually equivalent. Smooth, bounded, pseudo-convex. Then the Neumann operator N1 is compact if and only if P omega satisfies property P1. This was shown by Tristan Fu in 2005, I think, yeah. And this is actually, it's a very difficult, I think, at least it's a very difficult proof, but it's interesting. I don't have time to go into this at all, but these questions here in the context of these domains are related to properties of certain Schrödinger operators on the disk. In particular, the implications between compactness here and property P1 are related to what physicists call diamagnetism and paramagnetism. So it's just one of those things that, the real world crops up in a C2, in a problem in C2. All right. Well, now, let's come back to disks in the boundary. They are really a really obvious obstruction to property P1, right? And so the question is, are they always an obstruction to compactness of N1? And in general, this is open, somewhat surprisingly. It is true in C2, and it is true in higher dimensions under an assumption which is sort of clear that it shouldn't be there, but the proof requires it. So I want to discuss this. I'm going to start with part 5. So the first result I will discuss here is that one I've just mentioned. And then I will discuss a situation where everything meshes perfectly, namely the geometry, the potential theory, and the analysis, namely if the domain is a convex domain, then compactness of NQ is equivalent to property PQ and is equivalent to the absence of Q-dimensional varieties from the boundary. Right, so PQ is the potential theory, compactness of NQ is the analysis, and the presence or absence of Q-dimensional varieties from the boundary, that's geometry, if you will, the boundary. Okay. So let me state this theorem that deals with analytic disks. This, by the way, was proved by Sunmis Hartogs and myself. Sunmis was a former student of mine. So omega a smooth, so C infinity smooth, bounded pseudo-convex domain in Cn, let P in the boundary of omega be a point there. So let P and B omega. And assume, let's see, and assume B omega contains a disk, an analytic disk. Through P. Okay. If B omega is strictly pseudoconvex, in the directions transverse to the disk, just at the point P, but then this will be in the neighborhood. Right, so the tangent to the disk is going to be in the complex tangent space. Take directions transverse. If we're strictly pseudoconvex, then well, then things are okay. In the sense that we can prove that the Neumann operator is non-compact. Maybe a slightly more precise way of saying this, we look at the eigenvalues of the Levy form, right? And then the direction of the disk, you have a zero eigenvalue, and the other eigenvalues should be strictly positive, I guess is what I was trying to say. Okay. Well, we can get started with the proof, I think. Yes?
So the statement about the boundary is convex in directions transverse to the disk.
Mm-hmm.
This is nearly to, if in fact we didn't have that condition, presumably the Neumann operator would still be non-compact.
Well, that's the thing. That's a good comment, which I was also about to make, right? You should, I mean, clearly this condition should not be there because, right, if it's more flat, that should be even more conducive to non-compactness. That is exactly right. But so far, nobody has figured out how to, how to do that. And in fact, you will see in the proof, there is a step in the proof that is crucial, at least as of now. In that step, when you do the same thing that you said, what we're going to have to do is we're going to take a section and it's going to be strictly pseudoconvex. And in that step in the proof, when instead of strictly pseudoconvex in that section, you make it more flat, the step in the proof is more likely to fail, actually. So this is kind of a strange, this may be an indication that maybe this is not the right proof after all. All right. So, well, first, a simplification. One can always, well, first of all, the argument is going to be local, essentially. One can always, near the point P, one can always make a change, a holomorphic change of coordinates, so that the disk is actually affine. It's just a piece of a complex line, and one can do a little bit better. One can arrange it so that on this piece of the complex line, the normal, the real normal, is constant. So simplification, that can always be done. May assume that we have the following setup. So here's the Cn axis. The point P, of course, will be 0. We have this disk. We can make this disk the unit disk by scaling if we want. Then we have these other directions, C1 through Cn minus 1. And so that when let's define S, let's call it S0. I want to take this slice now where I intersect with Cn equals 0. So that's going to be something like this. And by the condition here, this will be strictly pseudoconvex at P. Right, we have, in this direction we have the 0 eigenvalue. The other eigendirections are orthogonal, so they're going to be in the C1, Cn minus 1 directions. Okay. Now, because the real normal is also constant along this disk, I can take a small ball here, let me call it B tilde, which has its center on the real normal, well, continued inside, so that I can slide this along the disk and stay inside of omega. In other words, I can have, well, maybe not all the way. Let me just take a slightly smaller disk. I can have a slightly smaller disk, D tilde, oh, B tilde cross D tilde should be in omega, I think, right? Yeah. I'm using here that the real normal to the boundary of omega is constant along this disk. Okay. So this is the geometric setup that we're going to use tomorrow. The key fact, and that's the one I mentioned where we're sort of making things flatter, goes in the wrong direction, is the following fact, which I'll list and then we can finish for today. Consider the restriction from the Bergman space of S0 to the Bergman space of P tilde. This restriction is not compact. That's going to be the source of non-compactness in the problem. And now, why do I say if we make things flatter here, that is the S0, if I make it more flat, this goes in the wrong direction. This makes the restriction more likely to be compact. Well, when is this restriction compact? The extreme case is when B tilde is relatively compact inside S0, right? When it's not relatively compact and it comes out to here, then sort of the thinner it becomes relative to S0, the more likely the projection is to be compact. Or, in other words, if you make the S0 more flat, this is going to be sort of thinner with respect to that more flat boundary, and so the restriction is more likely to be compact. So this goes in the wrong direction. That's an interesting dichotomy. I'm not going to give the proof of this. The proof uses, probably not surprisingly, the Bergman kernel function for both these domains. Of course, right, the Bergman kernel incorporates everything about the Bergman space. But in particular, we do need the, along the normal here, we do need that the Bergman kernel for S0 and the Bergman kernel for B tilde on the diagonal, that they have the same asymptotics. That is, they grow like what 1 over the boundary distance to the n plus 1. Well, it's actually n because we're in n minus 1, but plus, right? That is crucial in this argument. I mean, this is in itself an interesting question, by the way. You have two domains like this. When is this restriction compact? And this is not understood in the sense, I don't think anybody has anything near in necessary and sufficient conditions. I think in dimension 1, there are results that sort of a potential theoretic nature that sort of measure how thin or not or thick, as the case may be, this inner domain is relative to the outer domain and so forth. But in CN, I'm not aware of any sort of strongly conclusive results. All right, so this is a good place to stop. We will, I'll indicate the proof tomorrow and then do this other result on convex domains. Thank you.